Alright, what's up guys? In this video, I'm going to pick up with some partial differential equations again. We're going to be talking about the wave equation. So basically here, we're asked to show that the given function satisfies the wave equation, which I'm going to write down in just a minute. And what we're given here is our function v is equal to sine of akt multiplied by sine of kx. And we want to see if this function satisfies the wave equation. So if you've seen the previous video that I did on the Laplace equation, where we basically took a function and we computed the respective partial derivatives to see that or to see if it satisfied the two-dimensional Laplace equation. Well, essentially what we're doing here is pretty much the same thing, and so we'll start by first writing down the wave equation, and we'll take it from there. So the wave equation, just like the Laplace equation, just like the heat equation, is just a partial differential equation, and it's just simply d squared v over dt squared is equal to a squared multiplied by d squared v over dx squared. And that's our wave equation. So we approach it with the same strategy that we did when we were trying to show that a function satisfied that Laplace equation. So let's just begin with the partial derivatives. Obviously, we need the second order partial derivatives, so that means we've got to start off obviously by finding the first partial derivatives. And we'll start with the partial of v with respect to t. So we just take our function here. Now remember, for partial derivatives, in this particular case, since we're taking the partial with respect to t, that means that all other variables is treated as constants. Hopefully you remember that from Calc 3. All right, so let's look at our function here and see what we get. Okay, well, in that case, what we can do is we can bring out the ak. So ak comes out. Now, we need to take we're basically using the chain rule here. So this sine here will change to cosine, and the chain rule says that we got to keep that stuff in there. So we'll get that. And since we're taking the partial respect to t, we didn't do anything with the sine of kx, so we'll just tackle that back on the back end. So this would be sine of kx, because we didn't touch that. So that's going to be the partial of v with respect to t. Now we need d squared v over dt squared. And this one is not hard to do either, because essentially we need to do the same thing. The only difference here is that this time, again, we're not talking about taking the partial with respect to x in this case. So sine of kx is treated as a constant. We're only concerned with this part. So we're going to apply the chain rule again. Now we know if we take the derivative of cosine, let's just say with respect to x, we know we get negative sine. So what we're going to do is we're going to move the negative to the front, and again, applying the chain rule. The chain rule says, well, that goes back in there. Now we knew that when we took the first partial derivative, the ak came out. So what's going to happen is when we take it again, another a is going to come out and another k is going to come out, thus giving us a squared and then k squared if we multiply them, because a times a is a squared, k times k is k squared. Then we can bring them minus to the middle or to the front. So therefore, the partial derivative here would be negative a squared, k squared, sine. And the chain rule says, well, you put that back in there. And we didn't do anything with the sine of kx, so we leave that alone. All right, so that takes care of the first and second order partial derivatives with respect to the variable t. Now we just got to do it for x, and we follow pretty much the same process. So we need the partial of v with respect to x this time. Okay, so what that means is the t now is treated as a constant. Okay, so if that is the case, then what we'll get is k sine of akt. Okay, because we're treating sine of akt as a constant, and then this just essentially becomes cosine of kx, because when we take the derivative of sine, we get cosine. and we pulled the k out front. If I would have put like multiply by k, that's the same thing as me bringing it to the front. So that would be the partial of v with respect to x. And we just need the second order partial derivative now. So we need d squared v over dx squared. And much like for the first part, it's really not that hard to do. We follow pretty much the same process here. Remember, we're treating sine of AKT as a constant. So if we apply the chain rule again, we can bring the negative to the front because we know the derivative of cosine is minus sine. And if we did it again, the chain rule says, well, that'll stay in there. We'll end up taking the derivative of the inside, which would be k. So k times k is k squared. We can move a negative to the front. So therefore, d squared v over dx squared would just be minus k squared sine of AKT multiplied by sine of kx. And all we're using here is just the chain rule. Hopefully you remember this from first semester calculus. Even though we're taking partial derivatives, we're really just using the chain rule, which you guys learned about in first semester calculus. That's the way the chain rule is written, or it's written this way as well. So you take the derivative of the outside function, leave the inside alone, multiply by the derivative of the inside. So that's basically what we were doing for each of these, because these are composite functions, basically, which is a function inside of another function. So if we take all of that information we have, we know that a squared is going to be multiplied by d squared v over dx squared. So, well, that's just going to be negative a squared k squared sine of AKT multiplied by sine of kx. Okay, so that we know. So since we know that, we can say that, in fact, the equation that we're given up here, or the function that we're given up here, v is equal to sine of AKT multiplied by sine of kx, we can say that it satisfies the wave equation based on the information that we have. Okay, and just go back and look at what the part d squared v over dt squared is, and you can easily tell that our answer is correct here. So for the final answer, we'll go ahead and write it down. We can say that the given function v satisfies the wave equation. And that is how you do it. All right, so if you got questions, feel free to reach out to me. I will be more than happy to help you with any questions you may have. All right, guys, I'll see y'all next time.